Hi, everyone. Thank you for being here. My name is Preetham Chaudhary, and over the next 15 minutes, I shall give you the highlights of my paper, Monadic and Comonadic Aspects of Dependency Analysis. First, I'd like to apologize for not being able to present the paper in person at Auckland. There had been some visa complications, but I shall try to give you the highlights of my paper through this virtual talk. So let's begin. So let's start with the basics of dependency analysis. Uh, so can you, okay. So let's start with the basics of dependency analysis. So what is dependency analysis? So dependency analysis is the analysis of independence of one program from another. Though it's called dependency analysis, essentially it's an analysis of independence. So what do I mean by independence? So program P is independent of program Q if changes to Q don't affect output of P. So to understand this, let us look at a few examples. So next, I shall ask a few questions. We would have one program P and another program Q, and the question would be like, if P is independent of Q, and we assume a call by name evaluation strategy. So the first question is, if P is if secret, then 1 else 0, and Q is secret, is P independent of Q? The answer is no, because if secret is true, then P would output 1, and if secret is false, then P would output 0. So P is not independent of Q. Next, if P is this program, first 42y plus z, and Q is y, then is P independent of Q? The answer is yes, because it doesn't matter what y is, the output of this program would be the same. Next, P is this program, this lambda term applied to this argument, and Q is y. Is P independent of Q? The answer is yes. So again, you see, like, this function does not look at its argument, it just returns 42. So it doesn't matter really what y is. So why do we do all these analyses? What is the motivation behind dependency analysis? So it is useful in analyzing security. So for example, if Q is sensitive information, then so is P, because if the output of P depends on Q, so P reveals something about Q. So if Q is secret, Q equal to secret is sensitive information, then so is P. It is also useful in partial evaluation. For example, P here can be partially evaluated to 42 plus Z. So maybe we don't know the value of Z right now. Maybe after some time we would know the value of Z, but we can partially evaluate P so that when we know the value of Z, we can immediately return the output instead of doing the two computations after we have the value of Z. So next, it is also useful in erasure. For example, this program can be erased to just 42. We don't need to keep these extra arguments along with us. So next, let us look at the calculus for dependency analysis. So there are many calculi to analyze individual dependencies. We have the ASLM calculus for security. We have slicing calculi for erasure. We have many other, Smith-Volpano calculus. We have Fanning-Davies calculus, and a lot of them. So in the year 1999, Abadi and colleagues unified some of these dependency calculi into a dependency core calculus called DCC. Over the years, DCC has become the calculus for dependency analysis in type systems. So what is DCC? DCC is an extension of Moggi's monadic metalanguage with graded monadic type constructors, TL. So we know Moggi's monadic metalanguage. It is a language for analyzing effects. But by grading the type constructor T, Abadi and colleagues showed that we can use the calculus for dependency analysis. So what is TL? What does TL represent? So TLA represents the terms of type A that are L secure. So if we have T secret bool, that would be the type of secret booleans. So these L's, where do these L's come from? So these L's come from a dependency lattice, and this lattice model for analyzing dependencies goes back to Denning, Denning's work from the 70s. So let us look at an example lattice to understand how dependencies are represented through lattices. So here we have this lattice. It is a lattice for classified information in government organizations. So public is the lowest classification level. Then we have confidential, then secret, and then top secret. So the constraint is that anything about confidential information should not be revealed at level public. Anything about secret information should not be revealed at level confidential, and so on and so forth. So, but of course, confidential information can depend upon public information, and top secret information can depend upon any of the three lower levels. But something from above should not be revealed to something below. So this can be formalized as if L2 can depend upon L1, then we say that L1 is less than or equal to L2. This is an if and only if. So L1 less than or equal to L2 if and only if L2 can depend upon L1. So let us consider a few examples. So secret can depend upon public information, but not vice versa. Public information cannot depend upon secret information. So the soundness of dependency analysis can then be formalized in as this statement: if L2 cannot depend upon L1, then information from L1 should not interfere in outputs at L2. So we can instantiate L1 and L2 as secret and public. So information from secret should not interfere in outputs at public. So this is the soundness condition for soundness criterion for dependency analysis. So in DCC, dependencies are analyzed and soundness is formalized via a judgment called protection judgment. It is represented like this: L is less than or equal to A. What does this judgment mean? L is less than or equal to A means the terms of type A may depend upon L. So, if L is secret and secret is less than or equal to A would mean the terms of type A can depend upon secret values. The judgment is defined inductively, but I am omitting it because of time constraints. Now, this judgment is used in the crucial bind rule of the calculus. You can see the bind rule, DCC bind. So here we have a term of type TLA, and we pattern match it, and then we check that B can observe values of type L secure values of type A. So this is where the protection judgment comes into play. So if B can observe L secure values of A, only then we allow that value of A to be used in small b. So this without this protection judgment, this rule does not really work. This would lead to unsoundness. So next, the protection judgment is also used to formalize soundness. So the statement of soundness looks like this: if A can depend upon L, but L prime cannot depend upon L, and we have this function from A to TL prime bool, then when this function is applied to two different arguments, they should behave the same. Because L prime cannot depend upon L, but A can depend upon L. So at level L prime, we should not be able to infer anything about A. So here the evaluation relation is call by name evaluation. So next we look at the limitations of DCC and our contributions in this regard. First, DCC is mostly monadic in nature and it cannot capture comonadic analysis like lambda circ of Davies. Second, the bind rule of DCC is non-standard and relies upon an auxiliary protection judgment, as we saw. And the protection judgment does not have a clear foundation. So we address these limitations in our paper. How? We design an alternative dependency calculus, GMCC, that is inspired by standard categorical concepts. GMCC is both monadic and comonadic. GMCC is sound and complete with respect to a class of categorical models. And the categorical models motivate a novel proof of soundness for dependency analysis. GMCC under certain restrictions is equivalent to an extension of the terminating fragment of DCC. And via this equivalence, we can explain the protection judgment and the bind rule of DCC from first principles. And GMCC, when extended to GMCCE, subsumes both the terminating fragment of DCC and lambda circ. So this is a more general dependency calculus. So I shall now give you some key insights of the paper. So many researchers thought that DCC is just a graded monadic calculus. But we show that DCC is more than just a graded monadic calculus. How? So we developed GMC, which is the internal language of a bicartesian closed category with a graded monad over it. And we show that GMC under certain restrictions can be translated to DCC, but not vice versa. And the translation from DCC to GMC fails because DCC allows some comonadicity in it. So DCC is not just a graded monadic calculus. It is something more than that. But DCC is also not fully comonadic. Why? Because GCC, which is the dual of the graded monadic calculus GMC, cannot be translated to DCC. However, if we extend DCC to DCCE, we can allow full comonadicity in the calculus. And finally, we can show that this extended calculus, DCCE, is equivalent to GMCC, which is GMC plus GCC. And why do we go through all these calculi? What's the end goal and what do we get out of it? This equivalence shows several things. First, this equivalence shows that dependency analysis can be understood in terms of graded monads and comonads. Second, it shows that the protection judgment of DCC can be understood in terms of monad algebras. And third, it shows that soundness of dependency analysis can be understood in terms of existence of certain monoidal functors. So these insights tell us something more about dependency analysis and relates dependency analysis to standard categorical concepts and gives us new insights. So if you want to know more, you can look at the paper. This is available from the digital library. And we also have an extended version of the paper with all the proofs listed in the journal version, and it is available from Archive. I would like to thank you and conclude my talk here.
And the question is, thanks for introducing the topic. And dependency analysis has various application. Um, so such as determining when you can optimize based on diffuse, but you choose partial evaluation as a specific one. Any particular reason why, I guess?
Yeah, so I have also written a comment and I would answer it. So the reason I have used partial evaluation example is because the calculus, we introduced GMCCE, subsumes lambda circ of Davies, and it is a standard binding time calculus. So that's why I have included partial evaluation example for dependency analysis in the slide.
Mhm. So I was wondering, as I was listening to your talk, how far do you think this work is from having an impact on actual, compilers or static analyzers?
So it's mostly a theoretical investigation. So DCC has been very influential over the years as a dependency calculus, and several dependency analyses have been modeled on the basis of DCC. So what this work does is give DCC a more solid foundation from category theory, and makes several simplifications in its presentation. It's not any, so I haven't designed any practical language, but I hope that the theoretical basis that I have given would be useful for people when they go and design something in practice.